Hey, welcome back, class, to our ever-changing discussion about plate tectonics. I'm going to go ahead and share my screen with you, and then we can get busy. Be sure to get your pen and pencil out, pen, your notebook. You know, I like to look at your notebooks. So last time we discussed divergent plate boundaries, where two plates are going away from each other. Today, we're talking about two plates going towards each other. Also called convergence. And so we're going to talk about convergent boundaries. Before I forget, I want to mention that the link again, there's the link that I've set up for you guys. I sent it to you in an email, so you can always get these notes anytime you want. Don't forget about that. All right, so we talked about lithospheric crust, right? Oceanic is one type and continental. All right. So we got two types of crust we're going to talk about, oceanic and continental. Oceanic, I'll abbreviate as O. Continental, I'll abbreviate as C. Pretty easy. For convergent boundaries, we got three types, okay? The first type of convergence is oceanic crust meets oceanic crust. The second is oceanic crust meets continental crust. And third, you guessed it, continental meets continental crust. So, ready? Let's draw. You know, it's my favorite thing to do. So we're going to draw all three, but first we'll start off with ocean crust meets ocean crust. Okay. So get your pencil. It's not hard to draw these things. Just follow along with me. Just draw a couple lines, draw a couple more lines. And then I'm going to switch my color to blue real quick. And I'm going to put a blue line right there. The blue line is for our wonderful ocean. Okay. So two plates come together. I'm going to call this plate A, plate B. I like when you give plates names. You'll eventually name plates and tell me what kind of boundary it is. But for now, plate A, plate B. And when we talk about plates, we need to talk about the motion. When we talk about motion, it's in relation to the plate that it's next to, right? So plate A moves west when you're comparing it to plate B, or some example like that. Okay, so since we talk convergence, something's going to happen. One of these plates is going to sink below the other one. Why? Because one of them is older, colder, thicker, and probably leads to it's more dense. Okay, little arrow for more dense. So I'm going to draw that A goes beneath B. There you go. What happens to B? It acts like a bulldozer and kind of scrapes off A. So I'm going to bend it a little bit right there. There you go. You just drew two plates. Now we need the motion. So I'm going to put a couple arrows in that show motion, and then one down here to show the motion of this downgoing slab. Okay. Plate A is being subducted beneath plate B. Okay, so this area is called a subduction zone. Note all the terms. I'll need you to learn these terms as we go through the semester, and we'll be tested on them. So interesting couple things happen here in this scenario. I will switch colors again. When the slab goes down, when plate A is going beneath B, it drags down a lot of water with it, lowers the melting temperature of the actual rock. Oh, before I get there, what kind of rock type was it? Do we remember? If we remember right, this rock type is basalt. And also B, since our oceanic crust and oceanic crust, and we said that in general, most oceanic crust is basalt. There we go. So as the basalt and sediments above it are getting drugged down, they bring a lot of water with it, which tends to lower the melting temperature of rock. Remember, there's a lot of heat and pressure as it's going down towards the center of the earth, if you will. It'll never make it to the center, but it's going down. So somewhere along the lines, you see my red, it starts to melt. And we call that partial melting or flux melting, okay? Reasons for that is what I just stated, the lowering temperature of the melting temperature. So interesting thing, some of this material will start to move upward due to buoyancy. It's lighter than its surroundings. and it'll penetrate the existing plate B and eventually form a little bump called a seamount on the bottom of the ocean. Yeah. Another way to think about it is just a little baby volcano. And if you let it get big enough, guess what we've got breaking over the surface of the ocean? We have a volcano. So volcanoes are associated with subduction zones. That's interesting. You might ask, what depth was that, Jim? Where does that occur? Roughly, let's just put about 100 kilometers down. Pretty deep, okay? Pretty deep. Some of those other volcanoes can exist on A, and they would get scraped off as A and B meet, and you might end up with some extra material right here. So you're destroying plate A, but you may be adding terrains, is what we call it, to plate B, okay? What's also associated is this area right here, and this is a deep ocean trench. So trenches are always associated right there. That's the deep ocean trench. If you want a little 3-dimension, we can always go like this. Let me zoom this down just a little bit over. We'll add just a little dimension. Maybe that'll work better for you guys. So that's the plate. That's the other plate. And everything in here is trench. Okay. Deep oceanic trench. Think Marianas Trench. Pretty deep. Okay. One more thing to mention here while I'm drawing. What's also associated is you get a lot of earthquakes. So I'm going to put earthquakes. Earthquakes happen in solid material. We measure different seismic waves. We'll get to that when we talk about earthquakes. But you know that we can record earthquakes. What's interesting is at some point, all of a sudden, we don't record any more earthquakes. It's interesting. We'll get to that. Shows us the depth of a downgoing slab. Okay, so I'm going to put earthquakes down in orange so you don't forget that I've color coded it as orange. So what's associated with a subduction zone? Volcanoes, trenches, deep ocean trenches, earthquakes, flux melting. So let me show you an example. I know you want an example. So i.e., we're going to go with Japan. And when there's a series of them, more volcanoes that stick up, they form a system here, and it's called an island arc system. Okay. And I'll show you an example real quick. So there's Japan. You can see Japan right here. You see all those little red dots? Those are associated earthquakes. I haven't taught you yet. We haven't done the mapping of it. But this line with these little teeth here is the overriding plate. So Eurasian plate riding over Pacific plate. Another thing to notice is we're talking about plate A meets plate B. But there's also another scenario where 3 plates can meet. That's called the triple junction, and you actually have it right here. Eurasian, Pacific, and Philippine plate. Fairly interesting, fairly active. All right, let's go back to notes. So we did ocean to ocean. Fantastic. Let's draw a line on there. Let's do ocean to continental right now. We'll start off with the same kind of scenario. Oceanic crust, and then continental crust. You know, you've got artistic freedom right here. So continental crust, oceanic crust. Well, when we're talking about rock types again, if your oceanic crust is what rock type? Basalt. And we said earlier on in lab that we're just going to call this granite for now. Okay. Granite is definitely higher in silica than basalt is. So this slab over here, this basalt slab, is going to be denser. It's probably older. And if it's more dense, it's going to sink. So we're going to put that guy going down and going down. Maybe I need to adjust my continent a little bit. Okay. We need, what else do we need? We need arrows. We need plate A. We need plate B. Plate A. Okay, and motion of this guy right here. So interesting here too. As this downgoing slab drags water, it lowers the melting temperature, and guess what we end up with? Sure enough, we get a little flux melting right here. Yeah, some of it's going to go up. This time it's going to go through the continent. It might form a little blob right here, a little chamber of magma, if you will, and we end up with volcano right there. Yeah, helping to make that continental crust. This time basalt meets granite. So basalt plus granite makes a whole wide variety of things. Okay. In this case up here, when we said basalt and basalt, I guess my volcano is going to be basaltic. Probably, right? Basalt plus basalt. In this case, it's basalt plus granite. That's going to lead to a variety of stuff we're going to talk about in lab. Okay, so this is also going to be about, 100 kilometers down. You're going to have the associated earthquakes for sure. This whole thing is also called a subduction zone. You're also going to have your trench. Sorry, I got to put water in here. So there's my ocean right there. That's always helpful. You're going to have, as the continent overrides the basaltic plate, you're going to have a little, what we call accretionary wedge here. Accretionary wedge. And what that does is make the continent bigger, basically, as it scrapes off the downgoing plate. All right, a couple more things to add here. We've got your earthquakes, we've got your volcano, your accretionary wedge. Oh yeah, one last thing is, sure enough, right there is a deep ocean trench. Okay, so it's similar, but it's a little bit different. We get a little bit different rock type. So I'm going to show you an example. Here's the Cascade Range. That's a good example. Other examples might be the Andes Mountains, right? Look at this range all the way from Lassen Peak at the bottom of the screen, Mount Shasta, Three Sisters, Mount Hood, Mount St. Helens. Sure, many of you have heard of that, all the way up into the Canadian Rockies. We've got a chain of volcanoes right there. Okay, so instead of an island arc system, this is called a continental arc. We will call it a continental volcanic arc system. Okay, we got lots more to talk about on these topics, and I've hit you with a lot of stuff, but I have some homework for you. You love homework, so your homework is to draw the continent to continent example. I know you can do it. You don't have to be the best drawer in the world, however you say it. You don't have to draw the best in the planet. I'm not. I'm trying to do it on a computer screen. Do your best. I'm not judging you on your artistry. I'm judging you on the things that I've been talking about. Can you label it? Do you know the definitions? And we'll get more into it as things go along. So, key terms: subduction, earthquakes, trenches. Let's see, what else did we talk about? Don't forget about the 3 types of subduction that we're talking about, and accretionary wedge. And the other ones that I talked about. So turn your homework in on Tuesday, and I'll see you on the next video. Have a great day.